Hello everyone and welcome to TLE Eliminators post-contest discussions. This is Vibhaas and today we'll be discussing Leetcode's Weekly Contest 466. How is the contest, guys? Sorry for being a bit late. There's some delay. Yeah. Two questions. Yeah. Okay, hello everyone. Was the fourth repeated? I have no idea actually. I've seen similar questions before, but not exactly that. Okay, most people have done two or three questions. All right, let's get into them one by one, starting from problem A. But before we do that, just a quick announcement. As usual, our self-paced courses are live now. TLE Eliminators self-paced courses. They're split into 4 different levels. So if you want a structured and ordered way to competitive programming, if you feel unsure or if you feel stuck in your journey, then you should definitely check them out. They are very well, they're created by high rated cpers, and they teach you exactly what you need to know to up your rating. So it consists of more than 40 hours of recorded lectures, more than 100 plus curated practice problems, hints and video solutions for all problems, as well as doubt support and a leaderboard. So definitely do check it out. All right. Okay, going back to the questions. um yeah, so why didn't I record the last contest? Which contest are you talking about, Ahmed? Okay, so the first question is minimum operations to equalize the array. So let's just write that down here. Question one. Okay, you're given an integer array nums of length n. In one operation, we can choose any subarray and replace each element in that subarray with bitwise AND of all elements. So each element becomes the bitwise AND of all the elements. Return the minimum number of operations to make the all the elements equal. Okay, so subarray is a non-empty sequence of elements within an array. So for example, here nums is 1 and 2. Output is 1 because we can take the whole array, do the AND operation, and everything becomes 0 comma 0, right? Here in this example, the nums is 5 comma 5 comma 5. Since they're already equal, we don't need to do any operations. So the minimum number of operations to do is 0, right? So for this, I don't think much explanation is needed. The observation is simple. So observation is very simple. The idea is basically, since we can replace in an entire subarray with the bitwise AND, so our idea should be simply make 0 operations or 1 operation on the whole array. Okay, on the whole array, and the 1 operation will simply be to take the elements from 0 to n minus 1 and do AND of them, right? So that will make everything equal. So now in which case do we make 1 operation? We only need to make 1 operation if all are not equal, right? So if all elements are equal, then we need 0 operations. Otherwise, if all elements are not equal, our answer will be 1 operation. Okay, so that's all the solution to this problem. I don't think there's anything hard. The time complexity is big O of n. So now it only tests your implementation in your favorite language. I have implemented it in C++. You can see the code here. So for the array numbers, we go through each value in this. If the value at any point differs from the first element, right? If the value at any point differs from the first element, that means that there is more than one type of number there. That means that there are different numbers there. So the answer becomes 1. Otherwise, if this loop finishes, the answer is 0 because all the elements are equal to the first element. Okay, so that's all for this question. Yeah, today's questions were a bit on the easier side, I would say. Okay, so let's move on to problem B now. I think there will be no doubts in A as far as I can see. Okay, problem B. Minimum operations to transform a string. You're given a string S consisting of lowercase English letters, and you can perform the following any number of times. So what is the operation? We can choose a character C in the string and replace it with the next lowercase character in the English alphabet. Okay, and pay attention, we can replace every occurrence of this character with the next lowercase character in the English alphabet. Okay, return the minimum number of operations required to transform S into a string consisting of only A characters. Fine. And consider the alphabet as circular, thus A comes after Z. Fine. So we're given some examples. We have Y, Z. So the idea is change Y to Z and we'll get Z, Z. Change Z to A, we'll get A, and so on. Right? So question 2. Okay. So let's take an example string. Example. And let's say we have AA, EE, FF, GG, H, or maybe like MM, ZZ. Okay, so let's say this is our string. Now if we start at some particular character, like for example FF, we can convert all the FF to the next character. So after F in the alphabet there is G, right? So we can convert all the F's to G, right? So basically it can become GG, GG. Now so on, we can one by one convert all the G's to H, all the H to I, and so on, right? But we need to minimize the number of operations done. So basically what we need to do is we need to ensure that we start with the smallest character after A. Okay, what did I say? We need to start with the smallest character after A. Start with the smallest character in the string, smallest character in the string after A, and for example let's say the string started with E over here, right? So basically we want to convert all the E's to F's, then it will become, it will look something like this, all these F's, then we'll convert all of them to G, and then we'll convert all of them to H and I and J until we get M's, and then we can convert that to Z's, and then we'll get A, right? So basically the idea is start with the smallest character in the string after A, and we can do the following type of conversion, right? So let's say these are the alphabets, G, H, I, J, let's say X, Y, Z. So basically let's say the smallest character after A is D. So then we'll have to convert all the D's to E in our first operation. In our second operation, all the E will be converted to F. And in our third operation, all the F will be converted to G. All the G will be converted to H, and so on, right? So basically, in each operation, convert the current character to the next character. Okay, convert the current character to the next one, until we reach A, right? So all the X will get converted to Y, then after that all the Y will convert to Z, then after that all the Z will become A, right? So how much time will this take? How much time is this process going to take? Well, we can write it simply. We can say that this time will be the operations required, not the time, the number of operations required. The operations required depend only on the smallest character greater than A. Okay, depend only on the smallest character greater than A. Why is that? Let's take our string. Let's say we have AA and we have W, X, x y y z. Okay, so now for w to get converted to a, it will take w to x to y to z, something like this, right? Then a. So here it takes 1 2 3 4 steps. Now for x to get converted to a, it takes 3 steps. Same for y to get converted to a, it takes 2 steps. Z to get converted to a, it takes 1 step, right? So basically, as we go from w to x, then we can take all the x's along with us as well, right? So basically what is happening is the number of operations required will only depend on the smallest character, which is not equal to a, right? So that's all. We need to find the time taken by smallest character not equal to a to become equal, and then we can print that answer. So basically, for all characters, for all x not equal to a, find maximum time. So find maximum number of operations, find max of basically the character z minus the character plus 1, right? So we need to make the character equal to reach z, and then plus 1 to convert from z to a. So that's all is the solution to this problem. For all the characters, find the max of z minus x plus 1, and we can return that value. And the time complexity of this solution is simply big O of n. Right, so this is also pretty simple, so I didn't spend too much time. I just told you the solution directly. Let's have a quick look at the code. So we set the max value as 0 in the start, assuming it takes 0 operations. Then for each value x, if it's equal to a, we can just skip it. If it's not equal to a, then max will get updated. So max will be the maximum of the old max, and also z minus x plus 1. And then finally, we can return the max for the whole string. Okay, so this is this short and sweet code for this problem. It runs in big O of n. Any doubts? I solved 3 out of 4, yet my rank is 3000. Yeah, that's because this contest was slightly easier than usual. This contest was slightly easier than usual. Yeah. Thanks, Mini. Is number 4 a famous question? I don't know. I'm not sure. But yeah. What concept do I need for number 4? Mostly like brute force-ish. Yeah. Yeah, so it depends on how long you took to solve the 3 questions as well, right? I would expect almost everyone who knows basic programming can solve 2 questions, and anyone who has like maybe some experience with CP can try and solve 3 questions, because today's was slightly easier side. But yeah, they won't be able to solve it fast. Like me 6 wrong submissions. Yeah, probably last question took me a lot of long submissions. Yeah. I'm not sure how many wrong submissions I did on the last question. I took much more time than required for the last question. It wasn't also not that hard. Yeah. Okay. So any problems in any doubts in question B, or we'll move on to question C now? Should we move on to question C? Question 1 and 2 are very simple, so I expect that most people would solve it pretty fast. What rating problems to solve to clear OAs? As far as I know, about 1600 problems at most come in OAs. So about that much. Yeah. Okay, let's move on to problem C since I don't see much doubts. Okay. So this question requires a few observations. What Leetcode rating is good? Depends on what you're aiming for, but I would say 2000 2100 rating is decent. Yeah, that means I think 2000, 2100 on Leetcode is roughly like expert or specialist on code forces roughly, which is about decent, right? I'm not that familiar with Leetcode. Like I started only recently, mostly for the PCDs. Okay. So you are given an integer array nums with distinct elements. A subarray is called a bowl if it has length at least 3 and the minimum of its two ends is strictly greater than the maximum of all the elements between it. Okay. So we're given array. It has some special definition of subarray which is called bowl. The bowl must be at least length 3. The bowl's ends should be strictly greater than maximum of all elements in between. All right. Segment tree on C. Interesting. I'm not sure why a segment tree was thought needed, but yeah, it's not that complicated of a question. I feel like you know too many topics, and when you know advanced topics, you want to try and solve with advanced topics. Have I done D with digit DP? No, I did not use digit DP. I used brute force / binary search approach. Okay, so let's get back to question 3, right? So we need to break down this problem and try to understand it so that we can solve it. So basically they have given us this structure and we need to count the structure. And what is the structure? Structure bowl, right? And what are the properties of a bowl? The properties are that it has a length of at least 3, right? It's a subarray which has length at least 3. And second, min of a of L, a of R of the bowl is greater than all the elements in between, right? So it should be greater than all these elements in between. So these are the two defining characteristics of a bowl. So let's give some examples. So an example bowl will be something like 5, 3, 2, 1, 4, 7, right? So now this is a bowl because 5 and 7 are bowl. And similarly, let's say we have 10, 10, and then 3, 2, 1, something like this. This is also a bowl because the two ends are greater than all the elements in between. What is not a bowl? Examples of bowls, and examples of not bowl. Examples of not bowl. For example, if we have 5, 4, 3, 2, 1, 5, and again 5. Okay, now this is not a bowl because this element over here is equal to the ends, right? So this is not a bowl. Similarly, if we have let's say 7 and then 4, 3, 1, 1, 6, right? Again, this is not a bowl because this element is greater than both the ends. Similarly, if we have, let's say 8, 10, 3, 5, 7, this is also not a bowl because 8 is greater than 7 and all the elements in between should not be greater than 7, right? So we understood what bowl is and what bowl is not, and we know that bowl must have at least length 3, otherwise it won't have any elements in between, right? So there's no point counting them. So these are the definitions of bowl, and basically we need to count all the bowls, right? So basically what have we understood from the question? We need to count all the bowls, and because we're doing counting, right? Counting means it's a combinatorics problem. Counting should give you combinatorics ideas. And what is the expected time complexity from us? Because now the questions have become complicated, so we'll start thinking about what the expected time complexity is. And we can see that numbers.length is less than or equal to 10 power 5. So that means that we can do it in O of n or O of n log n. That will be valid. Okay, so O of n or O of n log n solution. Okay, so how do we count, right? Usually for all of these counting problems where we have to find some subarray satisfying some criteria. Okay, So you will see a lot of counting problems which are of this format. Okay, the counting problems will have this thing. There'll be some special type of subarray. Okay, it will have some special type of subarray. This subarray will be given some special properties. Okay, some special properties, right? And if it satisfies, then only it's that type of subarray. Then we need to count how many are there. Count how many are there. So this kind of a question is very standard type of thing which you see a lot of the time, and it has very, like, defined ways to solve it, like very logical ways to think about it. And the first main idea about solving such problems is to orient yourself. Okay, so the first step is orient yourself. And what do I mean by orient yourself is basically that you should figure out some element or value which you can keep fixed, and the other ones you can search for. Okay, because we need to lower the type complexity. So basically, keep, let's say, one end fixed and look for the other end. Okay, something like that we need to do. That's a usual way we do counting problems. For example, when we count pairs also, we sometimes keep one pair fixed, and then we count the other end of the pair, something like that, right? So here also we're going to do an approach similar to that. Okay, so yeah, how to improve in subarray type of problems, I'm explaining the thought process behind it right now, so follow carefully, Madhav. Right, so we need to orient ourselves, we need to figure out how to fix one thing and then think about something else. So while solving the problem, I also thought about fixing many things. I thought about fixing the left boundary, and then trying to find what are the possible right boundaries. But then that is not a great way of fixing. Here the correct way of fixing is basically, for each element. Okay, what do I mean by fixing? I'll show you. Okay, so basically what I mean is, let's say you're given the array, and let me just write an example array from their examples and then show you. Okay, so let's say we have 2 5 3 1 4, right? 2 5 3 1 4. What we're going to do is we're going to imagine that this element, imagine it is the L value of the bowl. Okay, imagine that this is the left value of the bowl, and we're going to see if we can find a proper right value. Okay, then if you try this is not a proper right value, because obviously this element is, there's only two elements here, right? And the bowl size should be at least 3, so this can't be a proper right element. Can this be a right element? No, because 3 is greater than 1, so it can't be a right element. And we can see that 4, okay, so 4 is a valid right element, and 5 is a valid right element. Everything in between is smaller, so this 5 3 1 4 is a bowl. Okay, 5 3 1 4 is a bowl. So basically what we're doing is we're fixing one element, and we're trying to find the right element for the bowl. Okay, so we're fixing the L value, and we're trying to find the right value. And this is the key idea of many counting problems, is that we orient ourselves or fix one thing, fix one value, and try to find the other value. How many possible ways there are to find the other value. Okay, so that's the idea, to lower time complexity in these counting problems. Okay, so in this one, how do we do it, right? So the issue we run to here is, let's say this was going to be the left value, then there can be many possible right values, right? So for example, there can be several right values, like let's say there was a 7 over here, 8 over here, 9 over here. Then there'll be a valid bowl between 5 and 7. There'll be a valid bowl between 5 and 8. There'll be a valid bowl between 5 and 9, correct? So then it will be very hard to find all of these and count them, right? So multiple bowls can be formed, right? Right? So that's the problem we're having. And how do we approach this? So how do we approach this is mainly making one observation. Let's assume the current element is equal to the minimum of the endpoints of the bowl. Okay, so it's minimum of AL and AR. Okay, so it's the minimum one in the bowl. Okay, so basically what I'm trying to say is, assume that my current element 5, if it forms a bowl ahead of it, then it is going to be the smaller element. Okay, so it's going to be the smaller element. So basically, let's say if 5 and 4 is there like this, then this bowl is not valid. Okay, this bowl is not valid. Okay, we're not counting these bowls. We're only counting balls where 5 is the smaller of the two. So for example, if it was 5 4 3 7, right, then this will be a valid bowl to count, because 5 is the smaller one, and then they have formed a bowl like this. Okay, so I hope you understand. Basically what I'm saying is, I'm going to count the bowls where current element, where ith element is left endpoint, and also the left endpoint will be less than or equal to the right endpoint. Okay, I hope you understand. So I'm going to be counting the bowls where the current element is left endpoint, and also A of L is less than equal to A of R. So these are the two conditions I'm going to keep to count my number of bowls. Okay, so now observe this. Okay, that for each value, each left value, there can be at most one right value which satisfies this condition. Okay, for each left value there can be at most one right value satisfying this condition. And let me show you some examples. So let me give you an array, 3 4 5 4 3 2 1, 3 4 5 4 4 2 6, and 3 4 5 3 5 6 7. Okay, so now let's take this 5 as the left endpoint, and also we need that it should form bowls where A of L is less than equal to A of R. Okay, so if this is taken as left endpoint, then in the first case we have no right endpoint. Okay, first case there is 0 bowls formed. Okay, 0 bowls formed. Now in the second case, there is a valid endpoint and it is 6, right? 6 is a valid endpoint, and therefore one bowl is formed, one bowl. And here also there is one valid endpoint, which is 5, and only one bowl is formed, because the reason is, if we extend it any further, if we go from 5 to like this, then this will not be a valid bowl, right? This will not be a valid bowl, because we already found a number greater than or equal to 5, correct? We already found a number greater than or equal to 5. So then it gives us easy way to count. Basically, to your left you can have at most 0 or 1 bowl if you follow this rule. Similarly, to the right you can have at most 0 or 1 bowl, right? So basically what I'm trying to say is, assume that ith element, okay, I'll write it formally so people who like reading formally can understand. Assume that ith element is an endpoint of the bowl, and the two endpoints of the bowl, the minimum of them, right? So the minimum, it is minimum of the two endpoints of the bowl. Okay, it is minimum of the two endpoints of the bowl, then there is only two options for ahead. Either it's 0 1 bowls to your right and 0 or 1 balls to your left. Okay, basically what is happening is, like I said, let's say your element is 5, then if there is any value greater than 5 which occurs, then this whole thing will form a bowl, right? This whole thing will form a bowl. Similarly, to your right side as well, if there is some value which is equal to or greater than 5, let's say 7, then this will also form a bowl. Okay, so at most towards your right side there'll be 0 or 1 bowls, and to your left side also there'll be 0 or 1 bowls, right? This makes it very easy to count. We simply need to check if towards your right or towards your left there is some value greater than equal to your current value. Fine, I hope people are following this. So basically the key observation for this here is, key observation, if you think of the smaller one of the bowl, if you think of the current element as the smaller one in the bowl, at most one bowl formed to my right, and at most one bowl formed to my left, at most one bowl formed to my left. Okay, or in other words, we just need to look for an element greater than or equal to u on the left. Look for element greater than or equal to u, current element on left, and greater than or equal to u on right, and these will form the bowls. These will form the bowls. Okay, and this also gives us, so it's not related to the question, but it does give us an interesting fact, which we can prove using this idea. At most there will be 2n bowls, right? At most 2n bowls. It's not necessary to solve the question, but yeah, it's an interesting fact which I felt like mentioning, that because of this reason there'll be at most 2n bowls, right? Because there can only be one to your right and one to your left if you follow this rule. If you assume that your current endpoint is the smaller one. My time complexity is big of n, so I'll just show you the code for this, right? So we need one element greater than or equal to you on your left and one element greater than or equal to your right. So how do we solve this? And to find element less than equal to a of I, as well as greater than equal to a of I on left and greater than equal to a of I on right, what is the approach known as? It's called the monotonic stack approach, right? So we need to use the approach of monotonic stack, right? And this is a very standard topic which is taught everywhere, I guess. So if you take TLE Eliminators course as well, I think it will be taught in, I guess, level 2, maybe level 1 itself, not very sure. And we can just Google it. Finding next greater element monotonic stack, right? So ideally, if you're solving the third-ish problem on Leetcode, you should definitely know this idea. So it's there on almost every website. So many websites it's there. Monotonic stack idea. Let's just open Geeks for Geeks, and you can see that, next greater element for every element is there, and it's just a very simple stack approach. Basically, the idea is that the top of the stack will maintain the last greatest value. So you can basically pop that off to find the next greater element, right? Without stack also we can find the next greater element, yes. But I guess the complexity would become more, right? Because I just need the next element which is greater than or equal to it. So what is your approach for finding it without stack, Prince Raj? So I'll just show you the code for the stack thing. Just a minute. Sublime, yeah. Okay. So for me, because I have enough templates, I just put I just have stack trick as a snippet on my Sublime text, because anytime I want to use it, I just add it and I just press tab, and yeah, I get it. So this is for greater than equal to, you have to write like this, and so I make it greater than equal to, right? So these two functions, just go through them. You can also make it a template or a snippet for your contest if you want. Basically what it does is it makes a stack, and while the stack is not empty, it checks if the top of the stack, if the current element is greater than top of the stack, then it will pop from the stack and it will set that element's next greater element as the current one and then pop. So this ensures that each element, if it's followed by an element which is greater than it to the right, then that element sets its value of next greater. Okay, so that's it. If you're not familiar with this, just Google this and then come back to the video. Pause the video right now. Go Google next greater element using monotonic stack. It will take you 20-30 minutes maybe to understand it. Then you can come back, because I'm assuming that most people would know how to find next greater element on left and right. Okay, so this is the code for that. Right. Yeah. Now one more thing to take care of is what if the bowl values are equal. Okay, so there's one last edge case remaining, and the edge case which is, what if the bowl values are equal? Okay, so let's say I have 5, 3, 3, 1, 1, 5. Okay, so my approach so far is basically like this, right? So count equals 0 for I from 0 to n minus 1. If there exists next greater element or greater than equal to element, sorry, next greater than equal to element to left, then I'm doing count plus plus. And if there exists to the right, then again I'm doing count plus plus, right? So this is my approach so far. It's going to be my approach so far. But the problem with this is, if I have a situation like this where I have like 5, 3, 3, 1, 1, 5, then this bowl will be counted twice. Okay, this bowl will get counted twice, and the reason is simply because once it is getting counted for this 5, and second time it is getting counted for this 5. Since both of them are equal, then they will say that this 5 is my next greater element. Similarly, the other one will say this 5 is my previous greater element, right? So the problem is that we are double counting the ones which are equal in value. Okay, so we're double counting the bowls. This current logic which I have written here, this current logic will double count the bowls which are equal in size. Double counts bowls with equal boundary, and for that only one small change we need to do is, let's only count them once, right? So we need to make sure to only count them once. So we will only count left greater than equal to, so we'll only count left greater than equal to, and for right we'll only count the ones which are greater. Okay, we'll only count the ones which are greater, because the ones which are equal to have already been taken care of, right? So if the next element is equal to, basically if like the right value is, if that number is equal to the nums of I, right, then we can just skip it, right? So that way we are only counting the one ahead of me. So I'll only count this one ahead of me, but I won't count this one behind me, since it's not greater than equal to 5. It's not greater than 5, right? So that's all we're going to do for this question. And I think, like, if you're familiar with next greater and previous greater stacks, then this question is very simple. If you get the idea, you can just code it out very simply. Especially since I already had the snippet, I coded out pretty simply. Okay. Wait, all values are distinct. Is that given? Oh, all values are distinct, so we don't really care about it. Okay, sorry guys. Damn. Okay. Right. Since all values are distinct, my mistake. All values are distinct. We don't about this much. Sorry guys. We don't care. We don't care to check equal, right? Oh, in that case, we can just solve it without stack. Also, we can solve it with arrays. Okay, sorry guys. So in the case that they're all distinct, in the case that all are distinct, we can simply solve it with true or false Boolean variables also. We just need to know, if some value is greater than me previously, a of I to left or right, and we can just count that directly. Okay, fine. In that case, the solution is much simpler also. Sorry guys, I did not notice that they're distinct. But yeah, in the case that they were not distinct, this solution solves it completely. So first I just make these two functions to get my stacks, and using the stack trick, I get my greater than equal to elements on the left and right. Then basically I set my count equals 0. If the element on the left is not -1, so the way the function is written is that if there is no element greater than me on my left or right, I put -1, right? So if it's not -1, also if the length is at least 1, that means basically at least 3 elements should be there, right? So if there's at least 1 element in between, then I increase my count. Similarly, it should not be -1, and the length should be at least 3 of the subarray. and also it should not be equal. So while checking the right side, I'm making sure that it's not equal, and then I'm increasing the count, and finally I'm returning the count. So this part is not required since all the elements are distinct. We might as well remove this, right? And to be honest, we can simplify the code a bit more because we don't need to keep track of which element it is. We just need to know whether it's a greater or less element present or not. But yeah, this is pretty much the code for the question. Okay. Yeah. Kavish, I did not understand your question. Can you repeat it? For need to pass first and last element because they need to be the answer. I didn't quite get it. I'll just write down my final code. So actually, because the elements can be distinct, cannot be distinct, the elements are all distinct, then this approach itself is the correct approach. Okay. So for every I, final solution, for every I, if some value to the left is less than equal to a of I, count plus plus. If some value to the right is greater, so you can use prefix arrays as well then. If some value to the right greater than equal to a of I, right? Sorry, it should be greater than equal to. Then again count plus plus. So you can use simply prefix array also to find the answer. Right, so my code is a bit more complicated than required. But yeah, either way you do it, my approach is also big O of n, and the prefix array approach will also be big O of n. Okay. I will not be doing today's div 3, someone else is doing it. Why no track of position? We need size at least 3. We are keeping track of the position. The position is here, right? So I'm making sure that the greater than equal to element at I is less than I minus 1. So that makes sure that the size is greater than or equal to 3 over here. As you can see, guys. Though this is for trek tails. In array based, how will you keep track of position? Well, in array based, let me just write the code right now itself. So if you want to do array based, then you simply need to find prefix array, suffix array, for suffix array max, prefix array max, and basically you need to check if prefix I minus 2 is greater than equal to a of I or not, right? This is what you need to check. Similarly, suffix of I plus 2 is greater than equal to a of I or not. Why? Because we need length at least 3, right? So in a prefix or suffix array approach, we need to check this one. Instead of stack based approach, if you do the array based approach with this, then you need to check ahead and below. You need to make sure that there are at least 3 elements. So that's how you'll do it in prefix array approach. This approach will also be big O of n itself. So the benefit of the stack based approach is that it's more directly implementing the statement, and that you can easily change it to handle non-distinct case as well. But yeah, since it's distinct case, it's much simpler to code a prefix array and suffix array rather than coding the stack trick. Yeah, Kavish, your idea is also correct. You don't need to keep the position. You can just keep the number and stuff. Like, obviously, it can be implemented many ways. As long as you have the core idea down that it should be the number greater than me on left and greater than me on right, it's correct. Yeah, all right. Let's move on to next question. I think everyone has mostly understood this. Time complexity we already discussed. It's big O of n, right? Okay. All right, then we'll start the next question now. I don't think I need to code the array based approach. You guys can do it. All right. So count binary palindromic numbers, and the problem statement is pretty simple. We just need to find from 0 to n how many numbers are there which are palindrome in binary form, right? So you're given a non-negative integer n. It's a binary palindrome if it reads the same forward and backward. we need to find how many palindromes are there. So basically, if n is 9, 0 is a binary palindrome, 1 is a binary palindrome, 3 is a binary palindrome, 5, 7, 9, right? And that's what we need to find. Okay, Pradeep and Remant, you can ask your questions toward the end of the session. We already started question 4. Yeah, Himanshu, the numbers were distinct. I did not read that actually. Like until the comments pointed it out, I did not even read it, not during the contest or now. When I read it, I realized the solution would be much simpler. Okay. So there's nothing much to say about this question statement. It's just direct question. How many binary palindromes are there less than equal to n? And also we need to find for n up to 10 to the power 15. Okay, so n should go up to 10 to the power 15 and we need to find the answer. Yeah. So since the number n is very large, obviously we cannot do brute force and check each possible n up to 10 to the power 15, right? So we need to find some clever way to do it. And one idea you can have is, so the first observation, okay, I'll tell you the first observation already. I want to ask how many of you thought of this. Is that since it's a binary palindrome, so let's say I have the number 111001010 and then it's a palindrome, right? So it will repeat on the other side. So we'll have, right, so this is an example binary palindrome. And why is it a binary palindrome? Because it starts repeating on the other side, right? As you can see, these two are same, these two are same, these two are same, these two are same, so on and so forth. If you see, write it forwards and backwards, it's the same. Or if you divide it at the midpoint, then all the elements across the midpoint are the same. Okay, so this is a binary palindrome. Now the interesting thing about a binary palindrome is you can only need to think about the one half. Okay, you only need to think about one half, because the other half is simply mirror image of this half. Okay, the other half is simply a mirror image of this half. So is that clear? So this is the first observation. Only care about half the digits. Okay, half the digits. So let's say we want to do a brute force approach. Then what we can do is we can brute force this half, and the values of this half will automatically get filled. Okay, I hope you're getting me. We can only brute force one half of the digits, and the other half of the digits values should automatically get filled. So let me just show you one code I wrote for brute force in the start. So I will explain the code in detail right now, but basically what I'm doing is I'm trying to brute force all the values and basically check if it's less than or equal to n, and I'm increasing the answer based on that. Okay, so basically what I'm doing is yeah. So what we're going to do is like temporary brute force solution or a brute force approach, right? We'll analyze the brute force approach later, but the first brute force approach we get is basically try for, like, assume it's first one digit. Okay, assume the palindrome is one digit. So let's just first generate all the one digit palindromes. Generate all one digit palindromes, all one digit palindromes. Then we'll generate all two digit palindromes. Then we'll generate all three digit palindromes and so on. Okay, so we'll generate all of them one, and what we're going to do is basically so to generate all four digit palindromes, for example, all we need to do is we need to generate 0 0 0 1 1 0 1 1, right? Then with this we get the palindrome 0 0, we get like this, and we get like this, and we get like this, right? Now these two are not valid, since this is 4 digit, this is 4 digit, but then this is 3 digits and this is 0 digits, right? So these two will not be valid, and only 2 of these will be valid. So only these two will consider. Okay, so I hope that much is clear. Yeah, so basically what we're doing is we're generating these palindromes, and we're going to try and count how many of them are less than n, right? So for example, we'll generate 5 digit and 6 digit and so on, and let's say n is of some d digits. Okay, so n has d digits. Let's say n is, let's say 1026. So then it will have maybe 10 binary digits, right? It will have 10 binary digits. So up to 10 digit palindromes we'll check. Okay, so that's how we're going to do it. And if we do this brute force, how much time should it take us? Okay, how much time should it take us? It should take us basically the amount of time needed to generate the second half of the bits. So that will be big of. So let's find what is the maximum n. The maximum n is 10 to the power 15. So that is 10 to the power 15. How many digits can this have at most? So this can have 50 digits at most, right? Because log 2 is 49.8. So at most it can have 50 digits in binary. So basically we can have at most 2 times 25 digits to brute force. Okay, 2 to the power 25 digits to brute force, which is roughly these many digits as our right half. In question 3, long was there for confusion. Yes. In question 3, I think long was there for confusion. The answer was always fitting in int. Okay, back to question 4. So these many roughly numbers are there, which is roughly 10 power 6, 10 power 6 around numbers to brute force on our left half of the number, right? So now you would say that, okay, since they're only like roughly 10 to the power 6 to 7 numbers to brute force, that ideally this should pass, right? Ideally it should pass, right? But I can tell you that I also got TLE with this. I'm not quite sure why I got TLE, but maybe what they're doing is they're expecting the constraints are tight, and because we have to use long over here, right, all the operations will be done in long while doing the brute force. That's why it's getting TLE. I'm not sure why it's TLE. Yeah, I guess like all the long approaches will make it a bit higher. Makes sense. So that's why it's TLE over here. Yeah, so basically we need to find a more efficient solution. But before we go to the more efficient solution, I just want to show you what the brute force approach looks like. Okay, and yeah, one more observation we can do is, let's say n is equal to some binary number like this. Okay, so some binary number, and it has 1 2 3 4 5 6 7 8 9 10 digits. Okay, n has 10 digits. So that means that palindromes which are of size 1 2 3 4 5 6 so on all the way till 9, all the palindromes of size 9, all of them will be smaller than n itself, right? And how many possible palindromes we can have? Basically, to have a palindrome of size 4, that means we have 2 binary numbers of size 2. Similarly, to have a palindrome of size 5, we have 2 binary numbers followed by a 1 or 0 followed by 2 binary numbers again, right? So total palindrome numbers, binary palindrome numbers with n digits or with d digits will be equal to 2 to the power d by 2, right? 2 to the power d by 2, because d by 2 up to we can choose, right? We can choose up to d by 2 numbers, or you can write ceiling of d by 2 for odd cases. So 2 to the power d by 2 and roughly half of these. Okay, so roughly half of these So that will be 2 to the power d by 2 divided by 2. Okay, or you could write it like this. So these are the number of palindrome numbers with d digits, and for all d less than the number of digits in n, so d is equal to number of digits of n, number of digits of n, simply add 2 to the power d by 2 minus 1 to the answer. Okay, so is this clear? Because the number of digits is lesser, that's why we are adding this value to the answer. And where did we get this value from? Where did we get 2 to the power d by 2 by minus 1 from? We got it because to form a palindrome of d digits, let's say we have d digits, then we can choose all possible combinations for the second half, right? We can choose all possible combinations of values for one half. So that's why this is 2 to the power d by 2 combinations. And why are we dividing by 2 again? Because this should always end in a 1. If it ends in a 0, then the leading digit will also become 0, so it won't be valid. So that's why it should always end in a 1. So that's why our answer is 2 to the power d by 2 by 2, or 2 to the power d by 2 minus 1. Okay, so that's why for a given digit d, we have these many palindromes of that digit. And so for all d less than d, we can simply add this value to our answer. Okay, so I hope this much is understandable. Right, this much is understandable. For all d less than d, we can simply add this to our answer. And for remaining, we'll try brute force. Okay, for the remaining, we can try brute force. And I tried that approach also, and that failed. So what is palin? Palin takes a value of b, which is equal to number of digits, and val, which is equal to right half, val which is equal to right half, and then what it does is it returns the palindrome of it. Okay, so basically what I'm doing is given some value for the right half. Let's say I'm given a value like 1100. So this is my val, and I know that I need a palindrome of number of digits 12. Okay, I need a palindrome of number of digits 12. So let's say I write this down: 1 2 3 4 5 6, 1 2 3 4 5 6, right? And I need a palindrome of 12 digits. So what I can do is I can write 1100 for the right half, then over here also 1100, and the remaining values will also be zeros, right? So this is how I make my palindromes. So I hope this is understandable, right? So for any given value of palindrome, we can brute force entire right half, and we can generate the left half of the palindrome, and then we can count them, right? So this is the brute force approach. Please just go through the code. If n is 0, so it's a brute force solution, right? So it's much more about implementation rather than much logic. So bitwise logic is being used here. So if n is 0, I simply return 1. Here bc is the count of digits, or bit count. So this is the bit count, number of binary digits of n. Initially my answer is 1. Why is it starting at 1? Because 0 is also a possible answer. Now for all binary digit for all palindromes with less than bit count digits, right? So less than the number of digits of the actual value. So for all palindromes with less than that, we can add all possible of them. So we're using this formula again: 2 to the power d by 2 divided by 2. So that's what I've implemented here. So I'm adding those. Now for every palindrome, every bc digit palindrome, right, I'm checking if it's valid or not, if it's less than equal to n or not, right? So it takes this value, it takes this number of digits, it's going to convert it into right half and left half. Basically, what is this logic? It's basically saying if a bit is set in right half, set it in the left half, right? In the left half. So this is generating the palindrome. it's right half and generate the left half as well, right? So that's what this code is doing, and it's checking if this palindrome which is generated is less than equal to n, then it increases the answer. So this is a brute force solution to the problem. Okay, and the problem with this is that this solution is also TLE. Okay, so please don't assume that this is the solution. I have not finished yet. This solution is also TLE. Okay, so this solution, although it saves time, this solution is also TLE. Roughly it takes maybe half of the previous one, so roughly it will take this much time, I guess. But since we're using longs, all the operations will be operations will be slow, so we can just multiply like a high constant to this. So basically it's taking too long to find the answer, but this is what my answer is going to be based on. Okay, this is what my answer is going to be based on. I have a function which can take the right half and generate the right plus left half, both of the palindrome, and I need to find how many are less than equal to n. Okay, so using this brute force, can you think of how to optimize it? Okay, so this is a question for the chat. Can you tell me some approach to optimize this brute force? My main problem is here, right? This is my main problem. My main problem is here, and the main problem is simply the fact that main issue for exactly BC digits, I am checking every value. I am checking every palindrome, if it's less than equal to n or not. Okay, if it's less than equal to n or not, and I'm checking every one of them, and that's why it's becoming TLE. So can anyone in the chat guess how we can reduce the time complexity of this? How to reduce time complexity of this? Here I'm doing a simple brute force for each value. Odd values I'm taking because it should end in an odd number, that's why. So for each value I'm increasing by 2, and I'm checking from 1 to 2 to the power 2 by 2. Yeah, okay, yeah, I think in the start of or middle of session I already said, but yeah, we can do a binary search. And the reason we're doing a binary search is simple, because do a binary search, right? Do a binary search because the palindromes we are generating, so the first palindrome we'll try will be 1 0 0 0 0 0 1, let's say. And the next palindrome we'll try will be something like 1 0 0 1 1 0 0 1, right? And the next palindrome we're trying is something like this, right? So this is one half, this is one half, and this is the other half. Okay, so this half we're always trying in increasing order. We're making sure to try this half in increasing order. So let's say we have 1 0 1 1 1 1 0 1, right? So at some point this will become greater than n, right? At some point this will become greater than n. So the last one will be 1 1 1 1 1 1 1 1, right? So at some point one of these palindromes is going to become greater than n, and what we're going to do is we're going to do binary search on this, right? We'll do a binary search on this. Fine, we're using binary search at which point did the palindromes become greater than n, and once we have that, we can simply add this much value to the count. Okay, so assume that at this point it became greater than equal to n, so we can add this many values to the count. Okay, so that's the basic idea. So let me just show you the code for this, then we'll discuss the time complexity. The palindrome function is almost exactly the same. It takes a value and the number of digits. This value is being set as our right half, and the left half is being set using the bitwise operations, and it's returning back the value. If n is equal to 0, return 1. Bit count is the count of number of binary digits, so that's here. Answer is initially 1 because 0 is also a possible answer. For all the b which are less than bc, so for all the number of digits less than the current one, all the palindromes are valid, so we're just adding the count directly. Now what we're going to do is we're going to do a binary search. Okay, so we have a left endpoint and a right endpoint, and what will be our left endpoint? Our left endpoint is going to be this value, 1 followed by these 3 zeros. So our left endpoint is 2 to the power number of digits divided by 2 divided by 2. So this is our left endpoint. Okay. Yeah, this is the left endpoint. Same value if you see. You can also write it like this. Right, floor of d minus 1 divided by 2. Okay, so this is going to be a left endpoint, which is this. And the right endpoint is going to be all ones over here. So that's this value for the binary search. Okay, so one left shifted by bc plus 1 by 2 minus 1. Right, so between this, between 2 1 1 1 1 1, we are going to do a binary search. So we find the middle value. If that palindrome is less than equal to n, then we can update our best value. Otherwise, we can update our left and right accordingly. Okay, so because it's monotonic, we can do a binary search by generating only less than n palindrome. Yeah. Now, once we have found our best value, which is the number of palindromes less than equal to n, we can simply add that. So best minus this L value. So best minus the L value plus 1. So those many palindromes we can add. Okay. Now what will be the time complexity of this? Let's analyze it. So time complexity. So at first we're simply finding the number of bits, and here this is O of 1 operation. So bit count. So this will be big O of bit count to find everything less than the bit count, plus this binary search which we're doing. And what is the time taken for this the palindrome function to generate a palindrome? The time taken for this is the number of bits. So that is again bit count times. So the check function works in bit count. And how does the binary search function work? Well, what does the binary search function do? It binary searches between 2 to the power bit count minus 1 time and 2 to the power bit count, right? So roughly the range will be something like this. The range will be log of 2 to the power bit count. Okay, so roughly this much. So that will be roughly 2 to the bit count times bit count. So the time complexity of the solution is big O of bit count squared. Okay, so number of digits, binary digits squared, time complexity is taking, because we're doing a binary search, and log of 2 to the power bit count is simply bit count itself. Okay, so I hope you know this, right? Log of 2 to the power n is equal to n. That is why log of 2 to the power bit count is written as bit count. So the overall time complexity is big O of bit count squared. For n equals 10 to the 5, what is the time? So the time will be roughly log of 10 to the power 5 squared, right? So the order of roughly 2000 for 3000 operations it will be. Okay. So for in terms of n, we can write it as big O of log of base 2 n squared. So this is the final time complexity for the solution. Okay. And what is our final approach? Our approach is basically let me just summarize it. For number of digits d, for number of digits d less than the number of digits in n, so d equals digits in n. Okay, digits of n, binary digits of n, simply add 2 to the power d by 2 to the answer, and for digits d equal to d in palindrome, we can binary search the largest palindrome satisfying this, then add the count of best minus start plus 1. Okay, so the number of palindromes which satisfy this, and then we find the answer and we return the final answer. The time complexity is big O of log of n squared. Okay, you can go through the code once, especially the binary operations. So if you're not familiar with binary and binary or, you should definitely go through those operations because they help, like how the palin function is implemented and how this binary search is implemented, why the bounds of L and R are set like this. It's easier to understand if you take a pen and paper and write it down and understand, rather than simply hearing the explanation. Okay, but yeah, this was the general idea for the problem. Kavish Paraswar, I'm not sure exactly what you're saying. The log is base 2, right? So we're taking log base 2. Can we get all these solutions in PDF? What exactly do you want? Do you want PDF of the codes? The codes will be added to the description. The codes will be added to the description of the video. Yeah, the code will be in 1 or 2 hours. The YouTube video description will be updated, and you can see the code. Okay, Sam Jones. Or if you want, you can just go to my Leetcode profile and check it out right now itself. If you want the code right now itself, so you can. This is my Leetcode account, and you can go check out the solutions right now itself. Here, you'll be able to see my past solves, right? Yeah. Okay, yeah, Pradeep, you had some doubt regarding problem C. You can ask it now. I will take general doubts or any doubts. Any/general doubts. Thank you, Sam Jones. Pradeep, what exactly prefix 1 do you want to ask? Do you want to ask something regarding problem C? I think the prefix solution we'd already discussed, right? There's nothing much to discuss about it. How to quickly know that sliding window question needs monotonic stack? It's not about getting to know whether it needs a monotonic stack or not. It's about getting to know that it needs you to find the greater element afterwards or previous, right? You need to know whether it needs the greater element afterwards or previous. Once you realize that, then you should get the idea that you should use the stack. Okay, once you realize that, then you should get the idea that you need the stack. So don't get it mixed. Okay, you need to understand the structure of problem, understand the structure of the problem, realize that you need next/previous greater element. Once you realize this, then the stack should come to your mind. Then the stack/prefix sum approach should come to mind. Okay, sorry, prefix max approach. Sorry, prefix max approach should come to mind. Okay, for that problem in particular. Fine. So that's how you're going to do. For every I was checking whether it can be my right hand or left hand. No, I was basically assuming that, yeah, whether it can be my right hand or left hand, and also the smaller end. So that was the main point for problem C. That's going to be the smaller one of the two ends. Okay. So where is problem C? Yeah. So the main idea was that I'm assuming that if it's my left end and also the smaller end, then the next it will stop at like 7, right? So that will form the only bowl. It can't form a bowl with 8 because 7 will be bigger in that case. Similarly, I will check back also if it can form a bowl. So yeah, I'm assuming first it is left hand, then it is the right hand, and I'm finding if it's possible or not. And also I'm assuming that it is the minimum one of the two endpoints, right? Because each bowl will have a minimum and a maximum endpoint, unless they're equal, of course. And that's why I'm checking this. And since the values are distinct, I don't need to check that. From where can I learn about prefix approach? So yeah, okay, so the reason, okay, so prefix cannot tell you the next greater and previous greater. Prefix max cannot tell you the next greater element, but it can tell you whether next greater element exists or not. Okay, whether there is any element, whether there is any element greater than equal to or not. Okay, because if the prefix value is smaller, then you know that for sure there is no element greater than me. So the stack approach can give you the exact position. Prefix approach cannot give you the exact position or the value also. Stack approach can give you the exact position and value, but the prefix can tell you that is there any element such that it's greater than me or not, right? So that's all is needed for the question. If you see, if there exists any element, we just add answer plus plus, right? So for problem C, we don't need a stack. We can just do it with prefix array. Yes, Pradeep, you are correct. In the prefix, I'm checking if prefix of I minus 2 is greater than array of I, then I do ans plus plus. Kamal Kotri, for digits equals D, please explain. Okay, I will explain for digits equals D once again. I'm assuming you're asking problem 4. So for digits equals D, let's go back. All right. See, for the case where digits equals D, then at some point, it will become greater than N, right? So let's say my N is, let's say my N is 35. Okay, my N is 35. So what is 35 in binary? 35 in binary, let's just get it. 35 in binary is something like this: 0, 1, sorry, 1, 0, 0, 0, 1, 1. Okay. So now for number of digits equals 1, number of digits equals 2, number of digits equals 3, number of digits equals 4, number of digits equals 5. For these we have no issues, but we will start having issues for number of digits equals 6, right? So now when we have number of digits equal to 6, what we're going to do is we're going to try the first value is fixed and then other values we're going to try. Okay, so let's try them one by one. So first we'll try 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right, so these are the values for the first half which are possible. Second half values will be mirror of these. Second half values will be mirror of these. Right, so these are the valid palindrome numbers with 6 digits. Now in this one is allowed, but this one won't be allowed, this one won't be allowed, this one will be allowed, because this is less than equal to 35, this is greater than 35, this is greater than 35, this is greater than 35. What my brute force code was doing was, it was checking each one of these, and it was checking how many are greater, and it was adding that to the answer. Okay, but the thing is, we cannot brute force through this because there's not enough time. So what we'll do is we will do a binary search. Okay, so at some point the element will stop becoming greater and will start becoming smaller than 35, right? Sorry, at some point 35 will become smaller than this palindrome, right? So we're going to find that point using binary search. Okay, so you must know some binary search for this. How binary search works: binary search this point, okay. And why does binary search work? Because this is monotonic, right? We made sure that the palindromes are monotonically increasing, because first we're generating 100, then we're generating 101, not 100 exactly. So this is 100, then 101, then 110, then 111. So we're generating the right half in increasing order in binary. That's why. So who asked this? Kamal Kotri. Did you understand, Kamal? Okay, yeah, Pradeep, nice observation. So for a prefix approach, 100 will be between. So yeah, you definitely need to check for that, right? Okay. So yeah, you're correct. You should ensure that. So you just need to write an extra if statement, Pradeep. So if I did not implement the prefix approach, right? I implemented the stack approach. So I forgot that something like this could happen. So yeah, in the prefix approach, if there is a value like 100 in between, you obviously need to check that. So for prefix approach, basically then problem C, prefix approach, prefix max approach, you should ensure that prefix of I minus 2 is greater than equal to a of I. This should be 1. And the second thing you should ensure that is a of I minus 1 should be less than min of prefix of I minus 2 a of I. Okay, so these two conditions together, if it's true, then only then you do ans plus plus in the prefix approach. So nice observation. Yeah, that's correct, I think. Yeah. Okay, so that's about it. I think we discussed problems A, B, C, D. A, B were very trivial this time. C and D were maybe somewhat interesting. Any other doubts, guys? Cool, Pradeep. Nice. Thank you for pointing it out. Question 4 was mostly like a brute force. I thought the brute force would actually work because there was only 10 to the power, and I thought about the research session. That's why you can see a lot of wrong answers from me on the fourth question. First 3 questions were very standard, I would say. Okay, so you're consistently solving 2 questions, but how do you increase to 3 and 4? Your growth is stuck. So my suggestion will be to practice these concepts which come often. Okay, so practice the questions which come often on the third question, and usually they are from level 2 or level 3 types of questions. So like you need to know some basic topics and be familiar with it, right? So the basic topics are so like first 2 questions you can solve without much knowledge as well, but then for the third question onwards you need some topics. So these topics should be strong for you. One, combinatorics. Okay, combinatorics should be strong. Binary search, basic graphs, like for example DFS, etc. Stacks, prefix array, stack tricks. Like for example, this one use stack tricks, right? Obviously sorting and ad hoc. Right, so these topics you should definitely learn. Basically TLE level 2 and level 3 topics, whether you learn it from TLE or somewhere else. Spend maybe 2 or 3 weeks learning each topic properly, then after that do some practice, and maybe in 1 or 2 months you can definitely start solving level 3 the third question if you practice right. That's about it. You need to know the topics and you need to know the stuff. DSU, I'm not sure if the third question requires DSU, but yeah, I have seen DSU sometimes. DSU is not that hard to learn, so just add DSU, I guess. I'm not sure if I'll consider it as basic graphs, but yeah, this is lower priority. Sometimes maybe, like rarely. I see it in question 3. Okay, so I hope that answers your question, Love, or Raymant. I'm not sure how to pronounce your name. Thank you, Pradeep. That's very kind. Any other questions, guys, or we'll end the session now? Pretty quick session, I think. Problem A and B were very simple. Problem C was somewhat standard, and problem D also, even though it was a hard to implement question, the idea itself was pretty simple, I think. All right, then I don't see any further questions. Thank you, everyone. Thanks for watching. Hope you learned something. Will I solve AdCoder beginner? No, I won't be solving AdCoder beginner. Yeah. Okay. Thank you and see you next time, guys. Bye bye.